Hey everyone, welcome back to The Explainer. Today, we're diving into something absolutely crucial in the AI space, unpacking the incredible breakthrough efficiency of Google's new Gemma 4 models. If you've been following the industry, you know that keeping models incredibly capable but physically small is basically the holy grail right now. Google just made a massive leap here, and we're going to break down exactly how they pulled it off.
So let's just start with a kind of crazy thought. What actually happens when you force a massive, gigabyte-heavy AI model to fit onto an everyday smartphone? And more importantly, does it just lose its mind in the process? Well, the short answer is no, and the long answer is honestly a masterclass in software engineering.
To figure that out, here's our roadmap for today. We're looking at 1. The AI size problem, 2. Shrinking models with QAT, 3. Testing Gemma 4 locally, 4. Memorizing tools with QLoRa, and 5. Training at enterprise scale. We're going to see how Gemma 4 scales from a tiny 2 GB phone model all the way up to a massive enterprise cluster.
All right, let's jump right into section 1, the AI size problem.
You see, we've got to acknowledge the elephant in the room. The core bottleneck with modern AI is that these models are just too huge. To give you some perspective, an original, uncompressed 26 billion parameter model like the Gemma 4 weighs in at a staggering 50.5 gigabytes. That is massive. It basically locks out standard laptops and everyday phones right from the get-go. You'd literally need a dedicated server rack just to load the weights into memory. So how do we fix this without lobotomizing the AI?
Well, that brings us to section 2, shrinking models with QAT.
What's super interesting here is how Google tackled this. They use something called Quantization-Aware Training, or QAT. Think of it like this. The old way, standard post-training quantization, is basically like sitting on a bursting suitcase to force it shut. Sure, you get it closed, but you're probably going to damage the contents, right? The data just gets crushed. QAT, on the other hand, is like carefully folding your clothes to fit the exact dimensions of the suitcase before you even finish packing. The model literally spends its entire training run practicing being compact. And the results? It's that 72% figure. By baking the compression right into the training process, these Gemma 4 models achieve a massive 72% reduction in memory usage. And the absolute best part, the real kicker, is that they retain near original performance. It's an absolute game changer.
When you look at the real-world impact, it's pretty immediate. You can now run a seriously powerful 31 billion parameter model locally on just 18 gigs of RAM. The 12 billion parameter model fits into a very accessible 7 gigs, and the E2B model, just 3 gigabytes. This completely democratizes what our everyday consumer hardware can handle.
But they didn't just stop there. Under the hood, Google engineered a custom mobile schema. They use pre-calculated static activations, which basically means your processor isn't wasting power scaling data on the fly. They employed targeted 2-bit quantization for token generation while keeping the core reasoning at a higher precision. Oh, and by optimizing the embedding in the cache, they actually brought the E2B text-only footprint down to less than 1 single gigabyte. Less than a gig. Okay, let's move on to section 3, testing Gemma 4 locally. Because, it's one thing to read a spec sheet, but how does this actually hold up in the wild? Well, someone tested it locally on a standard consumer NVIDIA RTX 3060. They gave the model this incredibly high-stakes, emotionally heavy prompt, asking it to act as a Congolese epidemiologist fighting an Ebola outbreak. And instead of throwing up a red flag and refusing the prompt because of oversensitive guardrails, it drafted this incredibly rich, humane, and exhaustive operational plan. And it did all of this running entirely locally on a normal GPU. Plus, and this is wild, the extreme compression hasn't messed with the model's multilingual knowledge at all. During tests, it flawlessly completed complex formatting tasks across 79 different languages without skipping a beat. We're talking perfect rendering of Arabic, Burmese, and complex CJK characters, all while keeping the formatting clean and consistent. It even gracefully acknowledged its own limits when it came to certain low-resource languages. The compression simply didn't ruin its global capability. All right, on to section 4, memorizing tools with QLoRa. So let's explore how developers are taking these deeply compressed models and making them even smarter. There's this huge inefficiency in modern AI where we constantly feed models these really long tool descriptions in every single prompt. Well, in a super fascinating academic study, researchers found that by fine-tuning models using QLoRa, essentially teaching them to learn those schemas by heart, they could drop the prompt's length dramatically. They took a bloated 2,400 token prompt and crushed it down to a description-free prompt of just 128 tokens. That is nearly a 95% reduction in input overhead. Just imagine the speed up. But the real question is, does it actually work? And yeah, absolutely it does. Despite having almost all of its prompt context stripped away, the fine-tuned, description-free Gemma 4 completely crushed the baseline model, the one that literally had the full tool catalog handed to it in the prompt. It jumped from an ADF1 score of 0.47 all the way to 0.635. Turns out, baking that knowledge directly into the adapter weights is way more effective than just stuffing it into the prompt text.
And the story actually gets even better. When you look at semantic judge scores, they confirm that these models absolutely excel in tool routing. The description-free models maintained incredibly high accuracy in server routing and tool selection, scoring over 4 out of 5. Basically, the model doesn't need to read the instruction manual every single time anymore. It just innately knows how to use its tools.
Finally, let's wrap up with Section 5, Training at Enterprise Scale.
Let's zoom all the way out for a second. How are these massive base versions of Gemma 4 trained in the first place, before they get shrunk down for our phones? To handle the absolutely staggering compute required to train a 31 billion parameter model, Google relies on managed Vertex AI training clusters. They deploy these heavy-duty A3 Ultra machines packed with H200 GPUs, and they tie it all together with high-throughput managed Lustre storage. That's what you need to handle the massive data read and write operations for those giant model checkpoints. But what's really fascinating about operating at this massive scale is actually hardware fragility. When you have that many nodes running 24/7 for weeks, things are definitely going to break. And a single node failure can literally derail weeks of expensive fine-tuning. That's why the system is built to automatically execute 3 crucial steps: detect, triage, and remediate. It is constantly monitoring for memory errors, triaging the specific failure, and automatically replacing the faulty nodes. The overall training job just survives and keeps on going, completely without human intervention.
And that brings us to the end of our explainer. We've journeyed all the way from massive enterprise Vertex clusters that can literally heal themselves, right down to a highly capable 1 gigabyte model humming along locally on a smartphone using Quantization-Aware Training. The barriers to entry for advanced, capable AI have literally never been lower. So I want to leave you with this final provocative question. With this unprecedented, accessible power now sitting right there on your laptop or in your pocket, what are you going to build? Thanks so much for joining me on this explainer, and we'll catch you next time.